You step onto an airplane, you start your car, you maybe even rely on a medical implant. We take it for granted, don't we? That the critical bits in these machines will just work, not just for a little while, but for millions, maybe even billions of stress cycles. It's almost mind-boggling engineering. And it relies on parts designed to last, well, practically forever. But what if forever isn't quite what we thought? Today, we're diving into a really fascinating area of material science, a very high cycle fatigue, VHCF, and we're zeroing in on how this VHCF stuff plays out when components have notches. Anything from a simple hole to maybe a complex thread. These seemingly small things can totally change how a material behaves, and ultimately how it might fail after an incredibly long time. So this deep dive is built around a really comprehensive review by Zuliani and colleagues. It's titled Very High Cycle Fatigue VHCF of Notch Specimens, a review. Our mission today, cut through the tech talk, give you the essentials, and maybe uncover some of those aha moments, why materials sometimes break in really unexpected ways after billions and billions of cycles. Hopefully you'll walk away with a shortcut to being well informed about this hidden world of ultra-long life parts. Okay, so let's kick things off. What exactly is very high cycle fatigue, and why is it suddenly such a big deal in, say, automotive and aerospace?
Well, it's become critical mainly because our demands on components have just raced ahead of our traditional understanding. For decades, fatigue research mostly looked at maybe up to 2 million cycles. That's 10 to the 6. We call that high cycle fatigue, or HCF. But now, think about modern engines. Aircraft frames designed for decades, medical implants, they need to last potentially into the gigacycle range. That's a billion cycles, 10 to the 9. This huge jump in expected life, well, changes the whole picture.
A billion cycles. Wow. So how is it different from the regular fatigue we already knew about?
The really crucial difference is how things fail. It's a fundamental shift. In conventional HCF, cracks nearly always start from the surface. A tiny scratch, some damage, an external flaw. But in VHCF, under these really low amplitude stresses, but over billions of cycles, cracks often start internally. They kick off from tiny manufacturing defects like non-metallic inclusions or little pores buried deep inside the material. These hidden flaws become the weakest link.
Ah, okay. So it's not just about how many times you flex it, but where it breaks after all that time. That internal starting point is key. Does this mean all our old fatigue theories are, like, useless now? Or can we adapt them?
That's the million-dollar question, isn't it? Because the failure mechanism is so different, many HCF models and theories really need careful reevaluation. We need
Yeah.
solid experimental proof that they even hold up in the VHCF regime. It's definitely not just a simple extension of the old rules.
Right.
And this gets even trickier when you throw in something as common as a notch.
Okay, notches, you mentioned those, like holes or grooves.
Exactly, simple geometric features. And what's really fascinating is how these everyday things profoundly complicate fatigue behavior way out in the VHCF region. These discontinuities, even tiny ones, can seriously reduce a material's fatigue strength. We call that the notch effect.
Okay, the notch effect. How do engineers quantify that?
Typically, we use something called the notch fatigue factor, KF. Think of KF as basically a penalty factor. It's the ratio of the fatigue strength of a smooth, unnotched part compared to the notched one. So a higher KF means the notch is having a bigger negative impact.
Got it. But you said VHCF makes it complicated.
It really does. Several key differences pop up that challenge how we usually think about notches. First off, when we do these ultrasonic fatigue tests, usually around 20 kilohertz to speed things up, the stress around the notch isn't static. It's dynamic, governed by elastic waves. This means the simple static stress concentration factor, KT, that we often calculate. It might not accurately reflect what's really happening.
Okay, so the testing method itself introduces complexity. What else?
Second, there's another really interesting shift in failure mode. Remember those type 2 materials like high-strength steels and titanium alloys? In smooth samples under VHCF, they tend to fail from internal defects.
Right, you said that earlier.
Well, add a notch, and the local stress increase right at the notch root can actually force the crack to start at the surface instead. It's like the notch overrides the material's usual internal failure preference in VHCF.
Huh. So the notch dictates the starting point, even against the material's natural tendency.
Pretty much, in many cases.
Yeah.
And finally, unlike an HCF, where we might assume notch sensitivity is fairly constant, in VHCF it can actually change. Often it tends to decrease as you go further out into the billions of cycles.
It decreases, so the notch becomes less bad over time.
Sometimes, yeah. It means simple assumptions just don't cut it for these ultra-long lives.
Wow. Okay, this is definitely more complex than I thought. If the failure mode shifts, the testing is tricky, and notch sensitivity isn't even constant. How on earth do engineers design for this?
Yeah, it's a major challenge. The main tool, as I mentioned, is ultrasonic fatigue testing, usually 20 kilohertz. It lets us get to those billion cycles in weeks or months instead of decades. But it brings its own headaches.
Like designing the test samples.
Exactly. For ultrasonic tests, the specimen has to be designed just right to resonate axially at 20 kilohertz. It's fairly simple for smooth samples, but for notched ones, it often takes a lot of computer modeling, finite element analysis, FEA, to get the shape spot on.
Okay, so sample design is tricky. What about measuring that stress concentration, the KT factor?
That's another big hurdle. Historically, most people just use the KT calculated for static, unchanging loads. It's easy to find formulas or use FEA for that.
But you said that's not accurate at high frequencies.
Right. It's like judging a race car's cornering ability while it's parked. It doesn't capture the dynamics. So researchers have developed dynamic approaches. They try to figure out the actual stress distribution during the high-frequency test. Some methods compare the peak stress to other points. Others look at average stresses.
Does it make a big difference which method they use?
It certainly can. Different ways of calculating KT can lead to different values for notch sensitivity, even for the same test data.
Ah, so comparing results between different studies could be misleading if they didn't use the same KT definition.
Precisely. It's crucial to know how they calculated CODI. Otherwise, you might be comparing apples and oranges, as they say.
Okay, that's a really important point for anyone reading this research. Methodology matters a lot. So let's get into the specifics from the review. What did they find when looking at different materials? Steels, aluminum, titanium? Any broad trends or weird exceptions?
Definitely some interesting findings and, yeah, plenty of nuances. A big general takeaway first. For most materials, notched or unnotched, there was no sign of a traditional fatigue limit out to a billion cycles.
No fatigue limit, so no safe stress level.
Pretty much. The material just keeps getting weaker even if it's very slow. This really goes against the old HCF thinking where we often assume a limit exists. There was one weird exception, a specific steel, 17Cr2Ni2Mo, that did show a fatigue limit, but oddly, only when it was notched, not smooth. Very counterintuitive.
Huh. Okay, what about the testing frequency? Does that ultrasonic speed mess things up?
Good news there, mostly. Many common materials, titanium, aluminum alloys, high-strength steels, generally aren't very sensitive to the loading frequency itself. So the results from those fast ultrasonic tests often seem to translate reasonably well to real-world, lower-frequency applications.
That's helpful. Okay, let's break it down by material type. What about steels?
For steels, it's a mixed bag. One study on bearing steel found the notch factor, KF, actually decreased with more cycles. The notch became less detrimental over time. Smooth samples failed inside, but the notched ones failed at the surface. Makes sense, the notch concentrates stress there.
Okay, decreased KF. What else?
Well, contrast that with a structural steel, where KF stayed constant but was higher in VHCF than HCF, meaning the notch was more damaging at longer lives. And then there's this really unusual case, S690QL steel, where the notch sensitivity actually increased with cycles. It even went above 1.
Wait, sensitivity above 1? How's that possible?
Yeah, it suggests the notch effect was amplified more than expected. Could be its specific fine-grain structure, or maybe related to how they calculated KT in that study. Still debated.
Fascinating. Okay, what about aluminum? Lighter stuff.
With aluminum alloys, again variations, one alloy, ENAW6056, was super notch sensitive. KF values over 6 for sharp notches, and it stayed high. Always failed from the surface notch.
6? That's a huge strength reduction.
It is. But then another common one, ENAW6082, showed KF decreasing with cycles. Notch sensitivity lessened in VHCF for that one.
So even within aluminum, it varies. What about 3D printed aluminum, additive manufacturing?
Ah, yes, AMLC10 The review looked at that too. The notch effect was definitely there, but KF was fairly constant. But the really interesting bit, both the plane and the notched AM samples failed from surface defects, especially in the as-built condition.
So for AM parts, it wasn't necessarily the design notch, but the inherent roughness or tiny flaws from the printing process.
Exactly. Those process-induced surface irregularities often became the dominant factor, more so than internal defects or even the intended notch geometry sometimes.
That has huge implications for AM part design and finishing. Okay, moving on to titanium, big in aerospace.
Titanium alloys also showed variety. TC21, for instance, constant KTEF in VHCF, failures starting subsurface for both smooth and notched samples way out at high cycles. Another one, Ti8Al111V, had complex behavior depending on the stress ratio. It seemed like fatigue and creep were competing. Its KF decreased with cycles.
Creep, like slow deformation over time.
Yeah, especially at certain temperatures or stress ratios, creep can interact with fatigue. And then there was AM titanium, TEGSIC-L4V ELI. This one showed very little notch sensitivity, especially beyond 10 million cycles.
Really, very little why.
It seemed failures were mostly driven by the random distribution of tiny manufacturing defects inherent in the AM process. The risk volume, basically, how much materials under high stress where a defect might be lurking, seemed more important than the precise stress concentration from the notch itself.
Wow, so for AM T6LO4V, the random internal flaws trump the design notch effect in VHCF.
It looks that way based on that study, yeah. Very different from the rod alloys sometimes.
Okay, one more superalloys, like inconel.
Yep, Inconel 718. Highly notch sensitive. KH was mostly constant, but did slightly increase under some conditions with more cycles. And like most others, no fatigue limit seen out to 1 billion cycles.
Okay, so connecting all these dots, it really seems like material type, how it's made, especially AM versus traditional heat treatments, it all plays a massive role. It feels like there's absolutely no single rule for how a notch behaves in VHCF, is there?
You absolutely hit the nail on the head. The variability is huge. There's no universal formula, unfortunately. And that's the core challenge. Despite all this experimental data piling up, reliably predicting the VHCF life of a notch part is still a major hurdle. We're still working towards a general, validated method that engineers can confidently use.
So what are they using now? Are the standard methods just not good enough?
Well, take things like the ISO standards. They're straightforward, sure, but they were validated mainly for HCF. They make assumptions like that fatigue limit existing around 108 cycles, which we now know often just isn't true for VHCF in many materials.
Right, the missing fatigue limit.
Exactly. Plus, those standards only cover a few simple notch shapes. Real components are way more complex.
What about just using that KF factor method?
It's simple, but it has drawbacks too. It often relies on that static KT value, which we know can be inaccurate for the dynamic ultrasonic tests. And critically, it usually assumes notch sensitivity is constant, which, as we've seen, isn't always the case in VHCF. It can go up, it can go down.
So if the standard methods have these fundamental issues, are engineers kind of flying blind when designing critical parts for really long lives? What's the risk?
Flying blind might be a bit strong, but there's definitely more uncertainty. It means relying more heavily on conservative designs, adding extra safety margins, or doing extensive, expensive, and time-consuming testing. But researchers are developing more advanced models. They show promise, but they also have caveats.
Like what? Any promising examples?
Well, there's the stress gradient method, SGM. It's kind of an adaptation of an older idea called the theory of critical distance, but tailored for VHCF. It showed pretty good accuracy, within about a factor of 3 on life prediction for Inconel 718.
Okay, factor of 3 is better than nothing, but still a range. What's the catch?
The catch is its applicability to other materials hasn't really been proven yet. It needs more validation. Then there's another one, a modified theory of critical distance, MTCD. It uses a weighting function and calibration. It achieved good results within about plus or minus 5% on strength prediction for a couple of titanium alloys.
Sounds good, but limitations.
Yeah, it was calibrated based on data at 106 cycles, not really deep into the VHCF regime. And it relies on some older material constants, which might limit how widely it can be applied.
Yeah.
It's not quite a fundamental physical model yet.
So summing this up, it sounds like progress is being made on the modeling front, but for engineers designing critical parts today that need to survive billions of cycles, they still need to rely heavily on actual physical testing, right? There's no magic formula yet.
Indeed. Not yet. These newer models are promising steps, absolutely, but they need a lot more experimental validation across many different materials before we can say they're generally applicable and reliable.
Yeah.
So yes, for now, rigorous testing is still king, and it's a very, very long cycle kind of testing regime.
Okay. We've really covered a lot of ground here. We navigated the super complex world of very high cycle fatigue, and especially how critical and sometimes really surprising the influence of notches can be. We've learned the old idea of a fatigue limit often just doesn't apply. Failure mechanisms can totally shift from the surface to deep inside the material. Notch sensitivity isn't necessarily constant, it can change over time. And the prediction models, still a work in progress, needing lots of validation. This whole deep dive really drives home how incredibly intricate material science gets when we push components to these extreme lifespans, from the tiniest internal flaw, smaller than you can see, to the shape of a simple drilled hole. Every single detail matters when you expect something to last, well, almost forever. It really makes you think, doesn't it? Considering how much we depend on things lasting millions, even billions of cycles, are our design approaches truly ready for this very high cycle future, or are we still playing catch up with the demands? And maybe the most provocative thought, what other hidden challenges might be lurking out there in those untested, ultra long life ranges for all the products around us? Something to definitely keep in mind.